This video we talked about what a reference angle is and how to find those reference angles. And I said that we can go backwards. We can take a reference angle and we can use it to find the initial angle. And so that's what we're going to do in this video. Given that we're going to jump right into some examples. Given that theta prime, which is representing the reference angle, is equal to 42 degrees, and that theta is in the fourth quadrant, find theta. And so remember that if we're given something in degrees, we want to continue to work with those degrees. Something is in radians, we're going to work with radians. We don't have to be converting back and forth. This first one's given to us in degrees. The first thing I'm going to do is just kind of sketch out what I'm looking at. I think it doesn't matter which way you're going, it's helpful to view the sketch. So we have an angle of 42 degrees. Now obviously that is going to have to be in the first quadrant. Reference angles have to be between 0 and 90 degrees. But what we're told is that it should be in the fourth quadrant. That means it should be down here. So remember what a reference angle is it's a measurement counting off of the x-axis. So really that angle wasn't up here. That was incorrectly placed. The angle is in the fourth quadrant. It's 42 degrees off of that x-axis. So if we think about how to write out that initial theta, there's many ways we could do it. Probably the easiest way to write out what theta is just to say, hey, we're moving in an opposite direction by 42 degrees. I can call that negative 42 degrees. And that is a correct answer. How else could I have done it? Well, I could have said, well, let's take the long way around. Let's go from the first to the second to the third to the fourth quadrant, taking that positive angle. We would have had 360 minus 42. That would have given us an angle of 118 degrees. That's also a correct theta. It's just said any fourth quadrant angle. So could I have actually taken a couple rotations to get here? I could have gone 360. I could have gone that is not 118. That is 318. 318 is a correct angle. So I could have gone 360 and then I could have gone another 318. That would have given me another correct theta. So we've seen this a couple times before. We know that we have these coterminal angles that continue to get us back to the same position. I can't forget about all those coterminal angles. They're all correct angles. So the way I can write that is by writing a plus 360 degrees times n, where n is any integer. So we use that stylized epsilon and then our integer symbol. And that's indicating that we can add or subtract 360 because n is positive or negative. We can add or subtract that 360 to the negative 42 as many times as we would like. And that way we're going to continue ending up at that same terminal side. That angle, theta, has infinitely many correct answers. And so this is the way that we would want to express that. We do want to indicate that we do have infinitely many correct. Now, there are a lot of times that we don't care about getting infinitely many things. A lot of times the reference angle, our goal is not to get to a reference angle or to get back from the original, get back to the original angle. It is to use reference angles in a way that makes our life easier in other calculations. When we're getting deeper and deeper into this trigonometric stuff, reference angles will simplify our lives in a lot of ways. So a lot of times we don't care that we have all these rotations. We've talked about the coterminal sides occurring over and over again. If I'm going to take the shortest path from here to here, I'm just going to get that negative 42. I'm not going to go around 5 times and then end back there. I'm just going to take that shortest path. So we might also want to force our theta into a given quadrant. And so here we have a problem that illustrates that. Given that theta prime, the reference angle, is equal to pi over 5, and that the theta is between pi over 2 and pi, find theta. So once again, I'm going to start with a picture. Let's think about where this is, between pi over 2 and pi. Well, pi over 2 is here, pi is here. So this is placing us into the second quadrant, and the pi over 5 is how much we're measuring off of the x-axis by, so this measurement would be pi over 5. And so that would be our terminal side that the angle is getting us to. So we always have to measure from this positive x-axis. We can come around like this, that would be perfectly acceptable. Using the same ideas as before, we could have gone backwards, that would have worked. We could have taken multiple rotations, we could have come around the blue amount, gone another 360, but now we can't do that. Now there's only one correct path because we are being told that theta must be between pi over 2 and pi. So what that does is it eliminates this red route. We cannot take that negative route now. We must take a positive route. We can't take anything with multiple rotations. So if we think about how to piece this together. We do know that from here to the pi, an angle of pi, or to the negative x-axis, that would be an angle of pi. We have stopped short by that original pi over 5. So if I subtract those, I get 4 pi over 5, and that would be my theta. It is equal to 4 pi over 5. Now, I've done both of these without actually referring to the formulas for the reference angles. If we remember those reference angle formulas, we can reverse solve. So let me go ahead and take a minute to show you those. So in the fourth quadrant, we said that we find a reference angle by taking the 360 and subtracting off the original angle. If we're in the second quadrant, we found the reference angle in the last video by taking 180 or pi and subtracting off that original angle. We could take these formulas and we could solve them for that theta if we wanted to. So I'd have to take my theta, I'd add it over, and I'd subtract my theta prime. And this should work. So if we take 360 minus the 42, we get back to the same 318 that we had done in blue a few minutes ago by referring to the graph. In our second example, we could take theta, we could add it over, we could subtract the theta prime, so theta should be equal to pi minus theta prime, which would mean we'd have pi minus the reference angle of pi over 5. That's exactly what we did, and we got an angle of 4 pi over 5. So we do see that it does not matter if we use the formula or if we take more of the intuitive approach where we draw out the picture. I am always going to go to this intuitive approach because I just don't have the formulas memorized quite as well. I feel more comfortable just writing it down, drawing it out, and recognizing how to get there. Now, both of these were relatively simple. We just took the x-axis and subtracted theta. Is that always going to happen? Well, no. Remember, if we're in the third quadrant, that's not how the formula works. So this time we have a theta prime, or a reference angle, of 2 pi over 7, and I want to place that between 5 pi and 11 pi over 2. So same as before, I'm going to start with that picture. I can't encourage you enough in this class. Draw out your picture. It's really going to eliminate a lot of simple mistakes. So 2 pi over 7 is how much we're coming off of the x-axis by, either the positive or negative x-axis, but we need to figure out which quadrant this is in. So 5 pi and 11 pi over 2, both of these are significantly greater than just a single rotation, than 2 pi. So we have some extra rotations on this, so let's figure out where it should be. Well, we know this is pi, 2 pi, 3 pi, 4 pi, 5 pi. So 5 pi would be over here, and then 11 pi over 7 is 5 pi plus another pi over 2. So 11 pi over, I said 11 pi over 7, 11 pi over 2 would be down here. So what we can see is we are going to need to be in that third quadrant. So 2 pi over 7 is how much I'm coming off of my x-axis by into that third quadrant. This amount right there, draw it out, is 2 pi over 7. So let's think about how we get there. Let me make that even clearer. I'll draw in my arrow in there. So that little 2 pi over 7 is right there, but remember, if we're measuring from the standard position, that means we're measuring off of the positive x-axis. So we've gone around pi units, and then we've gone 2 pi over 7 more. So to find our angle theta, theta would be equal to pi plus 2 pi over 7 more. And so we would get 7 pi over 7, and then another 2 pi over 7 would be 9 pi over 7. And that would place in the correct spot. That would be coterminal with the angle that we want. But remember, we need to make sure we're satisfying the criteria. We want to be between 5 pi and 11 pi over 2, and 9 pi over 7 is not there. So remember when we were counting out that 5 pi, how many full rotations did we need to make? 2 pi is 1 rotation, 4 pi would be 2 rotations, so we went 2 full rotations before we went that extra amount. So 2 full rotations would be an additional 4 pi that we need to add to this thing. Alternatively, what you could do is you could get to that 9 pi over 7 and just start adding 2 pi's till you get to the correct region. And so if we add the 4 pi to this, we would have 28 pi over 7 would be 37 pi over 7. We need the common denominator being 7. 8 pi plus 9 pi is 37 pi over 7. And so that will be our answer. Now, as we did in the last few examples, we saw that we could use our reference angle formula and manipulate it to get it to something we can use. So if we think about the reference angle in the third quadrant, that is theta plus let's try that again. That would be theta minus pi, because our reference angle is how much we are off of that pi by. So the reference angle is theta minus pi. So if we were to rearrange that for theta, theta would be equal to theta prime plus pi. And so notice, very different than before. Before we were just saying take 360 or take pi, subtract the angle. Here we're actually adding the reference angle to the pi, just rearranging the initial reference angle formula that we know from the last video. And so if we had done this, rather than kind of viewing it on the graph, we would take our reference angle, which is the 2 pi over 7, and then we'd add pi to that, and that would give us a 9 pi over 7. Now we'd run into the same problem that we did before. Notice that 9 pi over 7, same as before. That wasn't the actual final answer because we needed to put that in the right spot. We said there's 2 full rotations. So we would still need to add some 2 pi's until we got it to be large enough. If we added 2 pi once, we'd have 14 plus 9, 23 pi over 7. Not enough, right? That's not between 5 pi and the 11 pi over 2. So we'd have to add 2 pi again. And so 14 plus 23 would give us 37 pi over 7. And that would be the right answer. All right, let's look at one final example. Here we have a problem given that theta prime is equal to 19 degrees and that theta is between negative 360 and negative 270. Find theta. Okay. So the first thing I need to do is I'm going to sketch it out to think about where it is. Always start with your sketch. Negative 360 and negative 270. Negatives means I'm traveling backward. So negative 360 would get me back around to this terminal position. Negative 270 would take me to the positive y-axis, take me right here. So we're actually looking for something in the first quadrant, but using a negative angle. Now the reference angle is still the amount we're measuring off of the x-axis, but 19 can't be my final theta here. Even though, remember, we said with the reference angle formula, theta is equal to theta prime. That is only true for a single rotation that is between 0 and 90. So negative, this is not true. We need to have the, we'd have to get it to become positive first. So here, really, the best way to approach this one is through the graph. And what we can see is we need the negative angle. So rather than going positive 19, what we want to do is travel backwards to get there. And all that requires is a coterminal angle. We want it to end in the same position. We just need it to be traveling backwards. And so when we subtract that negative 360, we get negative 341. And that would be our answer. In this case, the angle that we are looking for is actually the same thing as the coterminal angle. And that would be true. We can say that with certainty for angles in the first quadrant, that reference angles will always equal a coterminal version of that original angle. It might have to take off some rotations or add some rotations, but here's our answer, the negative 341. So if we are comfortable with the definition of a reference angle, it is just using that definition to take us around our unit circle to place it correctly. We know that a reference angle is always measured from the closest x-axis. So if we're going from a reference angle to the initial position, we need to figure out which quadrant that position is in. And then we're just thinking about, well, how much do I count off of the x-axis, and then how do I count this from the positive x-axis, the standard position.